Hello everyone. Today we are going to explore one of the most foundational topics in AI. Okay, so the topic is problem solving with AI. So we are going to talk about how computers approach and solve problems just like the human mind, but it uses the structural logical methods. So by the end of this session, you will have a clear understanding of the different types of problem that AI encounters and how those problems are classified and how AI strategies differ based on the nature of the problem. Okay. Now, the topics that we are going to discuss here are well-structured problems, ill-structured problems, linear and non-linear problems. Then we're going to take an example and then we're going to talk about that example. Okay. So now we'll just go through one each of the topic. So first we will talk about the what is a what is the basic idea. Okay, so artificial intelligence has been extraordinary and is very effective in solving problems, but those problems are the structured problems. So exactly, so what is the structured or a well structured problems? So a well structured problem is one that has a definite correct answer, so a correct inference, where an appropriate algorithm or a method is applied. So these are the problems that occur commonly in our day-to-day life. Suppose think of problems where the rules of the games are very clear. So the input is known, the expected output is known, and we have an algorithm for it. So all these things are if available, then those problems are called as the structured problems. Okay. So in our day-to-day life, we are facing problems, but we do not realize whether it is a structured problem or it is an unstructured problem. So you take an example of solving a math equation. Okay, so a computer data packet routing and missile guidance, and then calculating the trajectory for the missile guidance. So all of these are the well structured problems. Okay, so these structured problems always, when it is going to be structured, they are solved with efficiency and accuracy. Next we will discuss about the uh, one of the we'll discuss about the characteristics, that is first always these well structured problems is a definite right answer, so there is no ambiguity, either you get the solution or you do not get the solution. So but still this makes it very straightforward that this particular well structured problem is going to give a right answer. Okay, secondly, all this will get a proper right answer only when there is an appropriate algorithm to be applied. Okay, if there is a proper algorithm applied, then we are going to have the correct result of it. Okay, so next we will talk about the the one of the another characteristics, like it is called as the uh, we call it as the evaluation. So we know exactly what success looks like, so there is no subjectivity in that. Okay, so there should be a clear evaluation criteria for it. And the fourth one is, suppose if there are similar problems, then there is going to be a similar structure for it so that we can generalize the solutions. Okay, so if you're taking an algorithm to solve one quadratic equation, the same can be used to solve other quadratic equations. So this is the power of the well structured problems. Okay, so next we will talk about the ill structured problems. So while ill structured problems are the problems which do not yield a particular answer. Okay, so there is a possibility that it can have more than one answer, and even a particular situation that decides the correctness of the answer. Interestingly, ill-structured problems represent many of the real-world problems that we will discuss one by one. Okay, so Okay, so this is a difference between the well structured and the ill structured problem. So always we know that a well structured problem will give a definite right answer, while the ill structured problem might have multiple answers. Here an appropriate algorithm must be applied. Here the situation decides the correctness. Here there should be a clear evaluation criteria. Here it is oriented towards a problem specific. Here the generalization can happen. In ill structure it is very difficult to generalize. Okay. Now we will talk about in detail about well structured problems examples. Okay. So already we know that problems that yield a right answer or a right inference when an appropriate algorithm is applied, those problems are well structured. So we will take the examples and we'll discuss. Okay. The first example is the quadratic equation. Okay. So when you're asked to find the value of x, okay, 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 right, in an equation, it can be any equation like x squared minus 5x plus 6 equals 0, any kind of equation. Okay, so you can use the quadratic formula, okay, then factorization or completing the square. So every method will give you the same result. So this is perfectly a well structured problem. So when you try to apply a appropriate algorithm, that is going to yield you the right answer. Okay, so always we know that for a quadratic equation, then there is a specific mathematical answer is existing. Now we'll take one more example, that is missile trajectory calculation. So when a missile is launched, its path through the air is governed entirely by the laws of physics. So it involves gravity, initial velocity, angle of launch, etc. So these are called as the deterministic factor. So given the inputs, the outputs, the trajectory can be computed precisely. So this is one of the correct answer. Okay. So these are some of the example of the well structured problem. Third, we will talk about the ball speed calculation. Okay. So when a ball is thrown towards a batsman in a cricket, so how is the speed being calculated at which it reaches the batsman? So it is called as kinematics problem. So the formula is very clear here. The variables are measurable. So you will get a precise output for that. Fourth one is the network flow analysis. So in computer science and telecommunication, network flow problems involve finding the optimal path or maximum data throughput in a network. So these are solved using well established graph algorithms. Like we can talk about Dijkstra algorithm, Ford-Fulkerson method. So likewise you have different algorithms. So these algorithms reliably find the best solution every time. So all four of these examples, what are the examples we discussed? We discussed about the quadratic equation solving, trajectory calculation, and then we talked about ball speed calculation, network flow analysis. So all of these four examples share one key property. So if you have the right input and right algorithm, then there is a correct answer obtained. Okay. Now we will talk about the ill structured problem and we'll take some examples. Okay. So what is an ill structured problem? Problems that do not yield a particular answer. Might be it is having multiple answers. Okay. So how will we do that? So we can take some examples of that. Okay. So they are completely different. Like already we said it is a multiple solution for that. Okay. For example, now let us take the one by one example on this and then we'll discuss how it is going to work. Okay, first is the waste disposal. For example, wet waste disposal. So, how should wet waste be disposed safely? It's very important. So, the answer depends on geography, local environmental laws, infrastructure availability, and even the weather conditions. So, there is no single universal procedure for how to dispose the wet waste properly. So, this is one of the ill-structured problems. So, second example involving theoretical proportions. So, in philosophy of law or social sciences, assessing a whether Assessing whether a theoretical argument is valid is highly subjective. Okay, so there are different experts reviewing the same argument may reach different conclusions. Okay, like third one is about the security threat identification. So threat is, to a larger value, larger public gathering. Suppose if you have a threat in a larger public gathering, okay. So a crowd at a music festival, anything political rally, a festival or a sports event, anything, any event you get it. The conditions change every minute. So no single algorithm can give you the right answer for it. Okay. So identifying the threats in the real time is going to be a very big challenge. So it requires contextual judgment, human intuition, adaptive AI systems working together. So all these involving together will give you answers every time, different answers will be obtained. Next, we'll talk about the challenges. So, no list of specific ordered steps exists. That's what we saw, right? That's what we saw, like we discussed in the previous. Okay. So, you cannot simply follow your procedure and find out the answer for that. Secondly, there is no well defined criterion to evaluate the correctness of the outcome. So every time there is a shift happening. So these two challenges explain why ill-structured problems remain among the hardest for all, among the AI systems to address. Progress in this space requires techniques like machine learning, fuzzy logic, and deep neural network tools that allows AI to learn from experience and adapt to ambiguous situations. Okay. Now we will discuss about behavior of problem types. Okay. So now we understood the definitions. Now we have made a comparison of well-structured and ill-structured problem. What was well-structured, what is ill-structured. Now we will try and see what is the actual behavior of these kind of problems, and we will try to evaluate or test for the solutions. So for a well-structured problem, the test has ordered steps. Okay, you can apply the algorithm, you reach a result, and the outcome is a binary. That is, the answer is either going to be correct or incorrect. Okay, so there is no gray area in this. So, but for an ill-structured problem, there are no ordered steps. Like you have an ordered step here, you don't have an ordered step here. Okay, so in the test, there is no ordered steps in the testing process. The evaluation directly go to the analysis part, and the outcome depends entirely on the context of the situation. So that is what we saw a lot of examples here, like the previous slides. Okay. So supposing if you are testing a solution to a quadratic equation, you substitute your answer back in and it either satisfies the equation or it does not. So it's black and white, it's direct. So if you're recommending a policy for reducing the urban crime, so you cannot simply substitute something like a quadratic equation. You will need to consider multiple factors like social factors, economical factors, historical data, possible feasibility, and so much you have to consider. Some experts might disagree, okay, whether this policy is correct or not. So it is very difficult for an ill-structured problem to give an answer whether it is correct or incorrect. So it will directly go to the analysis step. Okay, now we will talk about the abstraction portion, abstraction and generalization. So there is one more critical behavior, that is the concept of abstraction. Okay, for well-structured problem, abstraction is possible because you have ordered steps. Because the steps are well defined, you can generalize the solution and apply it across similar problems. That's what we said. Now, if we try to apply an algorithm for a quadratic equation, we can try the similar type of problems. You can use the same algorithm. The sorting algorithm works to sort any kind of number, all numbers. So this makes well-structured highly scalable. Okay. For ill-structured problem, the uniqueness of the problem, each problem makes generalization very, very difficult because each problem is different. You cannot abstract away the context, because the context is precisely what determines the answer. The demand is very high. Okay. So The distinction has profound implications how we build the AI systems. So for a well-structured problems, it can be based on rules and it is deterministic. For an ill-structured problem, it must be adaptive, probabilistic, and it should have the capability of learning from experience. Now let us take one example. Okay, like we'll take this tic-tac-toe problem. Okay, it's a well-structured problem because we know the rules. Okay, the tic-tac-toe is a perfect illustration. So what we have to understand here is, because I hope all know how to play this game, right? It's a 3x3 grid where two players are involved. So you can place X, O alternatively. Okay. Whomsoever the first player to get 3 in a row, simple, right? So from an AI perspective, this simplicity is what it makes so beautiful and well structured. Okay. See here the final decision is, it's based on these 9 positions of the board and the legal values, player 1 marked, player 2 marked and not marked. Objective is, solution tries to optimize the chances of player 1 and minimizing the chances of player 2. So thus a well-structured problem has a well-defined state space, clear rules and an optimal solution always exists. Now we will talk about the linear and the non-linear problems. So the linear problem is the one that has a definite solution. I mean, it has definitely a solution. Okay. So there is no ambiguity. In AI, these typically fall under the classification category. The key characteristics is that the relationship between the input and the output is linear. What is the meaning? Decisions can be separated by simple linear classification function. If you plot two categories of data on a graph and when you draw a straight line to perfectly separate them, then this problem is going to be a linear problem. So what's a non-linear problem? On the other hand, where the relationship between the input and the output is going to be non-linear. A straight line is not enough to separate it or to solve it. So these problems must undergo some form of transformation before getting a solution. Okay. So in machine learning, this is addressed using techniques like kernel functions, deep neural networks and polynomial transformations. Methods that effectively reshape the problem space so that the non-linears become separatable. We cannot separate it using a single line, right? So how you design the AI is a big thing, okay, big matter. So a linear classifier like logistic regression might be perfectly adequate for a linearly separable problem. But for a non-linear problem, you need to use more powerful tools. Okay. Next, we will talk about the comparison about well-structured, ill-structured, linear and non-linear. So, each has its own character, right? You can see. What is the criteria when you're talking about the answer portion? So, well-structured must have a right answer. It might have a multiple answers. It's definite or none. It requires transformation. Okay. Here, if you talk about the algorithm, you have to apply a specific algorithm. There is no fixed algorithm. You can use the classification function. Here, you need a nonlinear transformation. When you talk about the evaluation, it should be clear and objective. Should have an objective. Here, it is context dependent. It is linearly separatable. Here, it is not separatable. When you try to talk about the generalization, Possible via similarities, difficult to generalize. It's very straightforward, it is very complex. When you talk about the real use, it's used in maths, physics, networks. It's used in security, policy, and health. Here, text classification plays a role, and in image and speech recognition, we deal with non-linearity. So, finally, what are the key takeaways, or what is the summary? For an AI and structured problems, AI has been very well used to solve structured problems or a well structured problem. So, when an appropriate algorithm is applied, it definitely yields a right answer. Okay, so this is the foundation of the classical AI. Okay, well structured means predictable because their solutions can be generalized. The same method works for similar problems. So, this makes AI systems for well structured problem highly reliable and efficient. So, when you talk about ill structured problems, they are context dependent. Okay, so you don't have particular steps to solve it. Okay, so there is a lot of things you have to consider. You have to consider about the correctness, and it depends on the situation. Okay, so this is why these kind of problems that appears in real world are really a challenge to solve it. Next one is the tic-tac-toe problem. It's a well-structured problem. It's a classical example. You have a 3x3 grid where you have a clear rule specified and you get an optimal solution out of it. When you talk about linear versus non-linear, again linear problems have a different solution separatable by a linear function. So non-linear requires transformation. Okay. So the references are Stuart Russell and Peter Norvig and Parag Kulkarni. Thank you.